In this video, our attention shifts to solving indicial equations by taking logarithms. Though in previous videos, we saw situations where it was necessary to employ the use of logarithms to be able to get the final answer. But in this particular video, we are focusing on those instances where no matter how hard you try, you can actually not be able to make bases the same. So, and then logarithm will have to help you to uh, get the results. So let's go for that. Solving indicial equations by taking logarithms is the focus here. And okay, I guess this can go now. Okay, solving initial equations by taking logarithms. The learning outcome is that by the end of this lesson, you'll be able to solve equations of the form a raised by x equals b, then solve exponentially equations with mismatched bases, then use natural logarithm correctly, and then solve exponential equations that produce decimal answers and use a calculator efficiently for logarithmic solutions. Okay? So, in this case, we have a raised by x equals b. Normally, what we are used to solving is having maybe a raised by x equals a raised by y, where you can now say x is equal to y. But here, we are not able to do that. So let's go ahead and see when bases match. We want to have a quick review of that. When do bases actually match? If the bases are the same, like you have a raised power x equals a raised power k, then you can simply say that x is equal to k because the bases are the same, especially if the basis if a for is greater than 0, that is a is positive and it is not 1, right? So for instance, you have 2 raised power x equals 2 raised power 5. Now, since the bases are equal, we just say x is equal to 5 and that's it. So if the bases do not match, we have to use logarithms. That is the essence of this particular video. Imagine that we want to solve a problem like 2 raised power x equals 3. So how do we solve 2 raised power x equals 3? So since 3 is not a power of 2, so this 3 is not a power of 2, it's not like 4 where we could just say 2 raised power 2. So we take logarithms of both sides, right? So you have 2 raised power x equals 3. Then you take natural logarithms. So that's the log of 2 raised power x equals log of 3. Applying the power rule, we have x, for the law of logarithm. I mean, when we're still going to talk about logarithm, right? But one rule of logarithm is that when you take the log of a number with power, with an index, the x comes back, the power comes back. So you now have x ln 2 equals ln 3. Okay, and if you solve for x, it means you divide both sides by ln 2. So you have ln 3 all over ln 2. And this can also be written as log 3 base 2, which we've been working with even in previous videos. Okay, so we have this kind of issue here. All right, so the calculator workflow will be something like this. You type ln 3. Okay, maybe I can even demonstrate using this. So you type ln 3 divided by type ln 2, and you get this. So let's try that. So we have ln 3 divided by ln 2, and we get 1.585, okay? Approximately 1.585. It's the same thing when you say log to base 2 of 3. It's the same result you get. So ln 3 over ln 2 is the same thing as log 3 to base 2. Anyhow, you do that. But one thing that I'm curious about, let me check. What if I say what if I say ln to base 2 of 3? Does it give me the same results? No, it doesn't. Okay, that works. Okay, so at least we know these two are equivalent like this. Okay, so that's the workflow. So all we just need to do now is to take this kind of problems and deal with them. So imagine here you want to solve 5 raised to power x equals 2 raised to power x plus 1. So I'm going to solve this on a worksheet, by the way. So I'll just run through this and then go ahead and solve. So you start with 5 raised to power x equals 2x plus 1. So take natural logarithm. So you take ln 5 raised to power x equals ln 2 raised to power x plus 1. Of course, based on what we have learned, we know that ln 5 raised to power x means x will come back. So you have x ln 5 equals ln 2x plus 1. So x plus 1, which is the power, will come back and you have ln 2. And then we need to expand the right side. If you expand the right side, of course, on the left, you get x ln 5. On the right, you get x ln 2 plus ln 2. Okay? When you expand x times ln 2, x ln 2, 1 times ln 2, you have ln 2. Then what do? You collect like terms. So when you collect like terms, that means you have x ln 5 is equal to x ln 2 minus x ln 2 equals ln 2. So x ln 5 minus x ln 2, x is common. So you have x into ln 5 minus ln 2. And that is equal to ln 2. So if you can then solve and you get uh, x equals ln 2 all over ln 5 minus ln 2. And using a calculator, x is approximately 0.756. And the final answer is x is approximately 0.756. Okay, so like I promised, I'm going to do that on the worksheet. So 5 raised power x equals 2 raised power x plus 1. Okay. 5, 5, 5 raised power x equals 2 raised power x plus 1. Um, there's a way I don't, there's a way I just miss. Okay, this is fine this time around. Nice. 5 raised power x equals 2 raised power x plus 1. That helps. Okay, so here now we have 5 raised by x equals 2 raised by x plus 1. Now, the normal thing we would have done was, oh, is there a way we can write 5 as 2 raised by something? But that's difficult to come by in this case. So what we just do is we take the natural logarithm of both sides. So we have ln 5 raised by x equals ln 2 raised to power x plus 1. And from the law of logarithm, if we have log of a raised to power b. It's the same thing as b log a, b natural log a. That's one rule. Though we are still going to talk about logarithm later, right? We're saying that the log of a raised to power b is the same thing as b log a. Okay, natural log a is ln, right? So with this in place now, we can then say, okay, x, this x comes down, okay, and we have x ln 5, and that is equal to this x plus 1 also comes down. So we have x plus 1 ln 2, okay? So, and once we have that, we can say this is x ln 5, and that is equal to x times ln 2, that's x ln 2, okay? On the other hand, we have uh 1 times ln 2, that is simply ln 2 or 1 ln 2. That's ln 2 in short. So this is ln 2. Okay, that's natural log. By the way, uh, ln, I like to call it ln. I'm not sure if that's the best way to call it. Ln is log to base e. Okay, it's natural logarithm. So with this now, it's like this one has x, this one also has x. Can we bring them together? So we have x ln 5 minus x ln 2 is equal to ln 2 on the right hand side. So x is common here, so we have x into ln 5 minus ln 2. Okay, and that is equal to ln 2. So we need x now. We can divide through by ln 5 minus ln 2. So this is ln 2 all over ln 5 minus ln 2. So now we can get x to be a particular uh, approximated value. So ln 2 over ln 5 minus ln 2. So I go to decimals to do that. Ln 2, so I have ln 2 all over. Okay, no, that's not what I want now. What do I do now? Okay, I think, yeah, all over, no, ln 2 divided by, yeah, ln 5 minus ln 2. Yeah, something like this. So I have 0.756, approximately 0.756, 0.756. And that's the answer right there. So if you can check, you check. This is difficult to check because it's decimal, except if you have a calculator, you want to check. Okay, we have 5 raised power x and 2x plus 1. Okay, we can try. We can still try to check. So 0.756, right? So we have 5 on one side. So that's 5 raised to power x. That is, so we now say 5 raised to power, 5 raised to power 0.756. See that? So what we get. On the other hand, we have 2 raised to power 1 plus 1 at the power level plus 0 plus why? 1 plus, no, 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 no. Well, That's 1 plus x. That's 1.0.756. Okay, no, no, no. Something is wrong. 2 raised to power 1 point. And now 1 plus. Okay, it's not working still. Okay, 2 raised to power 1.0 point 1.0 1.756 rather 756. So yeah, you can see they are pretty close. So that's an approximate result. And it's correct to like the to two decimal places. Okay. So that's what we get right here. 0.756. And that's also what we obtain on the worksheet. I mean on the notes. So back to the notes, you see the answer is approximately 0.756. So in essence, if we are saying that if you're solving e raised power kx, the other time we solved a raised power x equals a raised power x equals b, right? That's x indicial, that's exponential still. But here now we have the base as e. E now is approximately 2.718, but a can take any other number, right? So solving e raised power kx equals a now. So if you're given that e raised power kx is equal to a, so we take natural logarithm since the ln is the inverse of e. So in this case now, we have ln of e raised power kx equals ln a. So you simplify, you get kx equals ln a, and solve for x, you get x is ln a all over k. Okay. What that simply means is that now, when you talk about exponents, right? When you talk about indices, we are used to having things like a raised power x, in the line of say 2 raised power x, 3 raised power x, 5 raised power x, and all of that. On the other hand, we can still have e raised power x, things like e raised power, yeah, things like that, e raised power x, e raised power 3x, e raised power. So now the e here, maybe e raised power 7x, anything. So in this case now, while a while a is like 2, 3, 5, and so on, e is fixed. E is simply it is approximately 2.718. Okay. Um, E is approximately 2.718. 2.718. So that's the difference here. Such that if we then have e raised power kx equals a, all right. So you need to understand that the uh the inverse of e is ln. Okay, because ln itself is actually log to base e. Okay, so they are inverses, so they cancel themselves out. So in essence, if you have e raised power kx equals a now, so you take the natural log of both sides. So ln e raised power kx equals ln a. Okay, and as a result of that, kx comes back. So we have kx ln e, and that is equal to ln a. So already I told you that ln e equals 1 because ln and e are inverses, so they cancel themselves out. So that's 1. So it means that kx, okay, is equal to ln a. And what you're looking for is x, right? So you divide through by k. So x on its own is ln a all over k. Okay? So you can have exponents in terms of some general value a raised power x, or you can have e raised power x. So these are possibilities. So this a can be any number, whereas, I mean, this a can be any number, whereas e is fixed 2.718. Okay? So, um, so based on that now, we can solve problems like this. You have e raised power 3x equals 7. Now this is not 8. E fixed as 2.718, and it's the reverse of the natural logarithm. So if you have e raised power 3x equals 7, take natural logarithms. So you have ln e raised power 3x. So 3x comes down, so ln e is 1, so it's gone. So you just have, so once you see this, if you're answering an objective question and not theory, so you don't have to stress yourself. Just take ln of both sides in your mind, and that just drops to 3x, and that's equal to ln 7. And then you can solve, and then you have so you divide both sides by x, I mean by 3. So you just know that ln 7, x is equal to ln 7 over 3. If you use a calculator, ln 7 is approximately 1.946 divided by 3, you get approximately 0.649, and the answer is approximately 0.649. So you have ln 7 over 3, right? Ln 7 over 3. Okay, so I just have ln 7 divided by 3. Okay, no, that's not what I want. So I have ln Maybe it's better to do lane 7, then I can then divide by 3 easily. Yeah, I think it's better this way. So that's 0.649 approximately, and that's exactly what we have around here. So let's talk about exponential equations producing decimals. So we have exponential equations producing, yeah, just like everything we're doing has been producing decimals. So it's just more like emphasis. So you have 4 raised power x equals 7. So take natural logs. So of course, take natural log, you have, now this is not e, this is a, right? So in this case, you have x lane 4. So nothing disappears here. If it was e, you just had x equals 7, and that's the answer. So if you had e raised power x equals 7, take log of both sides. So you just have x equals 7, and that's it. Okay. So, oh, sorry. If you had 4x e raised by x equals 7, that would have been x equals ln 7. Yeah, sorry. So take natural log. So x ln 4 is ln 7, and then that means x is ln 7 over ln 4. And that's 1.946 divided by 1.34386, and that's approximately 1.404 easily. And then you can also do the same for this. You have 10 raised by 2x equals 15. Take now, because this is power 10 now, you can then take, we have, when we talk about logarithm, right? We have things like this. So when you talk about logarithm, we have popular logs, like we have um common logarithm. There are two main types of logarithm. We have common logarithm, okay? We have common logarithm, that is log to base 10, okay? Say log x to base 10 if you like. Then, oh, we are still going to talk about log, by the way, so we'll get there. Then we also have the natural, or what you call the Napierian logarithm. We have the natural or Napierian logarithm. Okay. And what is that? That is simply log x to base e, which is the same thing as the ln x we've been talking about. Okay. So since if you can have since 10 is appearing in this situation now, you can actually use the idea that common log is also easily can be easily found. So you have log 2x, log raised by 2x equals 15. So you can take log to base 10. So you just have um log to base 10. Okay, well, I think I need to do this, right? So 10 raised by 2x equals 15. So to make it clear enough, log raised by 2x equals 15. So we have okay, we have 10 raised by 2x. 10 raised by 2x equals 15. Because this one is base 10 now, so we can easily take log to base 10 on both sides. So we just have log to base 10. Log to base 10, is usually shortened as log. So that'll just be log x. So if I use log and I don't indicate the base, we just assume it's base 10. So we can have other bases like log 2 base something, but these are the most popular, right? Log to base 10 and log to base e. Okay, so now log to base 10 of 10 raised by 2x is equal to log to base 10 of 15. So like I said, even if you don't write the base, well, everybody understand that it's log to base 10. So in this case, now you just have 2x log 10 to base 10 equals log 15 to base 10, right? So, and one law of logarithm is that log of something to the same base, log 10 base 10 is equal to 1. That's what was happening with ln e, because it's actually log e base e. That's why it was 1. That's why it cancel itself out. So when we get to log, you'll understand that better. So this is basically 1 now. So we then have 2x equals log 15. So I'm not putting the 10 because once you see log like this, it's natural log. I mean, common log, which is log to base 10. So x now is log 15 divided by 2. So that means x now is going to be approximately log 15 divided by 2. We are getting ahead of ourselves because we're still going to talk about log later. So now I'm doing log 15, log 15 divided by 2. That's approximately 0.588. Okay. Uh, so you don't want to mix up these logs because you can easily it's easy to mess them up. So you need to know the difference. Approximately 0.588 is what x is in this situation. So the deal here is because you see 10 here and it's very close to it's like you can easily deploy common log, but the same rules apply for all logarithms, whether it's common or natural. Okay, so we have 0.588 here approximately. And then we have So the systematic method here, the exam strategy, if you are dealing with solving initial equations using by taking logarithms, right? So when you see a raised power f of x equals b raised power g of x, different bases now. So follow this structure. Take logarithms, like natural log is safest normally, but if you see base 10, you can easily take 10. Then use the power rule. We know that already. Then expand the brackets, collect terms containing x, factor out x, and solve the resulting linear equation. Approximate if required. In summary, we are simply saying that if a raised power x is equal to b, then x itself will be ln b over ln a, because you take ln a raised power x equals ln b. So that's x ln a equals ln b. So divide both sides by ln a. So you have x is equal to ln b over ln a. Now, if e raised power kx is equal to a, then um, ln e raised by kx, ln e is 1. So you have kx equals ln a. So divide both sides by k, you have x is ln a over x. When bases do not match, what do? Take log both sides, use power rule, and then solve linear equation. Power rule means that if you take the log of a number with the has power, the power descends, the power then multiplies the log of the base, right? So as usual, I'll answer like 2 questions here if necessary. Practice problems. Solve the following. Give exact answers in logarithmic form where appropriate. Then give decimal answers correct to 3 decimal places. So from 1 to 10 now, let's see which one I'll go for. Okay, I'll go for the one that look it's not hard, but it looks the hardest, right? So 2 raised power x plus 1 equals 7. Okay, 2 raised power x plus 1 equals 7. So we go for that. 2 raised power x plus 1. 2 raised power x plus 1 equals 7. Okay. So yeah, we take the natural logarithm. So we have ln 2x, I mean ln x plus 1 equals ln 7. Okay, that means we have ln. Okay, I'm using the power law now. So x plus 1 comes back here. So we have x plus 1. So because it's two, you have to put the two together. You have to put it in a bracket so that you can know that they are together. So if you just write if you just write it as x plus ln 2 alone, that would be wrong. So we have x plus 1 ln 2 this way equals ln 7. And what exactly we want here is to solve for x, right? So you can expand the left-hand side. You have x times ln 2. Ln 2, that's x ln 2. Then 1 times ln 2 is ln 2. That is equal to ln 7. So now we have x ln 2 equals ln 7 minus ln 2. That's if you split up the, I mean, if you collect like terms. So that then means that x, you divide through by ln 2. So x is equal to ln 7 minus ln 2 all over ln 2. Okay, so we can use our calculator now. X is approximately ln 7 minus ln 2 all over ln 2. So let's go for that. So we have okay. Lane 7. Okay, there's lane 2 here already. So I just add to this. So lane 7 minus lane 2 all over lane 2. Yeah, we have that result. Lane 7 minus lane 2 all over lane 2. That's approximately 1.807. 1.807. 1.807. That's the result we get. It's harder to check in this case, but we can always check, right? Okay, I mean, just try 2 raised power 1.807. Is it close to 7? So that's how to check using your calculator. 2. So let's try 2 raised to power 1.807. 2 raised power 1.8. Oh, what's that again? I think it's not just 2. It's the original problem is 2 raised to power x plus 1, right? 2 raised to power x plus 1. So it has to be 2 raised to power 1, x plus 1. That'll be this now, plus this plus, okay. Or maybe if I put it in a bracket, it will work better. Plus 1, aha. So this should work. Okay, this is not working. So what if I put it in a bracket? Put it in a bracket. This, this. and this can go. Yes. So that's 6.99. I mean, to one decimal, to the nearest whole number, it's 7. To the first decimal place, it's 7. To the second decimal place, it's 7. To the third decimal place, so that's basically 7. So it's that actually works. 1.807 does the job of so if you check it around here, we're saying 2 raised power 1.807 plus 1, which is 2 raised power 2.807. So, and we see it's approximately 6.998. Okay. So, and that's to the nearest whole number, or to the first decimal, to the second decimal place, it's still 7. So that works very well. So we can check regardless. Okay. Now, regardless of whether it's decimal or not. So let me do another problem from 11 to 20. Which one looks the most difficult here? Okay, I think the last one looks the most difficult. 3 raised power x plus 1, 4 raised power x minus 2. Okay, 3 raised power x plus 1, 3 raised power x plus 1 is equal to 4 raised power x minus 2. Take the natural logarithm. So ln 3x plus 1 equals ln 4 raised power x minus 2. So bring down the power. So you have x plus 1. Don't forget, put them in brackets. So you have x plus 1 ln 3 equals x minus 2 ln 4. So don't forget, you are solving for x, right? So you can expand this. We have x ln 3 plus ln 3. When you multiply 1 by ln 3 by 1, then you have x ln 4 minus 2 ln 4. Okay, then you can put the x's together. Um, so we can have ln 3 on the left hand side plus 2 ln 4 right here. Okay, and that is equal to x ln 4 minus x ln 3. So what I've done is I brought this over here and I brought this over here so that we have x ln 4 minus x ln 3 here, and then um, this ln 3 here plus 2 ln 4, those ones without x, right? That's what I did there. So this comes here. So ln 3 plus 2 ln 4, because it was minus here, then x ln 4 minus x ln 3. So what do we do? Let me change the color here. Say we now have ln 3 plus 2 ln 4 equals x is common, so x into ln 4 minus ln 3, like this. So we are looking for x. So x can be isolated if we divide 3 by ln 4 minus ln 3. So then we have x to be ln 3 plus 2 ln 4. By the way, 2 ln 4 can also be ln 8, because the 2 can come back. Well, it's okay if we also leave it this way. Then we have ln 4 minus ln 3. Okay, so we have ln 4 minus ln 3. So then calculator comes in. Ln 3 plus 2 ln 4 all over ln 4 minus ln 3. Okay, ln 3, ln 3, ln, I can put this in brackets even. Ln 3, ln 3 minus 2 ln 4 divided by ln 4 minus ln 3. Oh, so it's negative this time around. So that's minus 5.819, approximately minus 5.819. Okay, this now. It is approximately minus 5.819. Can we check that? Yeah, we can, because we have 3 raised power x plus 1, 4 raised power x minus 2. Okay, 3 raised power x plus 1, 4 raised power x minus 2. 3x plus 1. So we have 3 raised to power, can put this in brackets, x plus 1, right? X is minus 5.819 plus 1. We have that. And on the other hand, we have 4 raised to power x minus 2. That's minus 5.819 minus 2. Okay, let me check again. 3 raised to power x plus 1, 4 raised to power x minus 2, 4 raised to power x minus 2, 3, 3 raised to power x plus 1, 4 raised to power x minus 2. Okay, 3 raised to power x plus 1, 4 raised to power x minus 2. They look a bit apart. So check and let me see what you think the problem may be. And if that is it, I mean, it's the approximate solution. So there can be a lot of errors in the process for sure. So this is how this has been. By the time we do log, you'll understand some more uh, complex ways of handling this whole scenario. So there might be a mistake or there may not be, but you want to check and confirm. Let me know your comment. Put it in the comment section if have made a mistake or not. All right. All right. So with this, I come to the end of this video. So don't forget to try your hands on the exercise. This is 1 to 10. Okay. And then this is 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. Um, if you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, the question is why? Why? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Okay. And having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges, like getting to see some videos first, or being the only one seeing some certain videos as members of the channel. Or we can also hang out to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.